So those 5 steps that we did for the formate ion, those 5 steps that we're going to do for tomorrow's lab, we're going to do them right now, right here. And so tomorrow's lab, I don't know how long it'll take us. It's not ever a race, but it might not be too bad. Okay, so let's look at how we would assemble those 3 atoms, 1 carbon and 2 oxygen atoms. Your first step is always going to be to come up with a pot of valence electrons. And so this is where I do a carbon colon. There's 1 carbon atom. It's a 4A element. And I mean, I don't have a whole periodic table memorized. You probably figured that. But I know carbon's 4A. So it has 4 valence electrons. And, you'd need to maybe look on the periodic table if you haven't been teaching it for 12 years. And then the oxygen atom, there are 2 of them. And oxygen is found in 6A. So collectively, they bring 12 valence electrons. Okay, so that is our pot of valence electrons. Well, not quite. Let's add them together. So we got 16 electrons to what we say distribute. So these 16 valence electrons, okay, are going to have to go on our Lewis structure somewhere, somehow. Step number 2, actually, I don't know if it's 2 or 2-3, I'm not sure, is to arrange the atom. And what I'm going to remind you tomorrow, or if you read it in tomorrow's lab, you always put the, like I said, the lowest electronegative atom in the center, in middle or center. Okay, so your options are carbon and oxygen. So electronegativity increases going that way, so oxygen's higher, so carbon's less. And it's kind of a symmetry issue sometimes, and you're like, oh, well, that makes sense anyway. So we're going to put carbon in the middle, and we're going to draw a preliminary Lewis structure. Okay, this is just kind of getting started. Where just like we talked about recently in lecture, anytime you see that is a covalent bond, and so think 2 electrons, right? So we have a covalent bond between that center carbon atom and these, we call these terminal oxygen atoms, Okay, so right now, and we're going to use this number, can you see on this preliminary structure, we have 4 electrons represented. So let me write next to, I'll put a semicolon, right next to that 4, I can write the word remaining electrons. I'm going to do a little subtraction, right? Our pot of electrons was 16, minus 4 here. Okay, so we have, wow, 12 electrons remaining to do something with. Okay, so this is where actually we're on to step 4, and step 4 of 5, so that's pretty cool. Okay, step 4 says, of those remaining electrons, go ahead and take care of your terminal atoms. Of course, we have the oxygen atoms are terminal atoms. What that means, take care of them, is to go ahead and give them a complete octet, okay, if possible. So here we go. Well, I think I'll go ahead and change. Well, I'll change colors here in a minute. Okay, so I'm going to redraw the preliminary structure. And now I'm going to go ahead and, right now, that preliminary structure, they only have, each oxygen atom is only sharing a pair of electrons with the central carbon atom. So you're like, dude, it's only got 2 electrons there. If it needs 8, we got to go ahead and divvy up 6 more electrons around each. Merry Christmas. Okay, so that's step 4. That's distribute the remaining electrons from your pot that wasn't on your preliminary structure around the terminal atoms.
This is nice.
Uh-huh.
How come oxygen doesn't need to use in the 6th column?
It is in the 6th column, so it has 6 valence electrons. So I used that number up there. I don't know if that was your question. So this is group 6A. And then what would, that wasn't your question though.
No, like, okay, so I know that you need 2 more to oxygen to get it to a full octet. So why did you put 6? Why wouldn't you just put 2?
So right here, it only has 2, and it needs 8.
So it doesn't originally have 6?
Well, see, it basically gave it 6 up for the pot, for the cause.
Okay.
Once it throws those 6 in a pot, who knows where they go. but they have to show up in the final Lewis structure. So yeah, you kind of forget about it once you start down the road. So you okay with this then?
Yeah, that makes sense.
All right, cool. So step number 5 may or may not apply, and actually this time it does apply. So step number 5, if you read your kind of 1 through 5 for tomorrow's lab, says go ahead and give, I'm going to go ahead and say, I'll make it this way, give the central atom octet. It probably goes more like make sure it has a complete octet. Sometimes it already has a complete octet by this time, but you can see carbon, not a complete octet. In fact, carbon has, let's see, 2 and 2. Carbon only has 4. So here's where, and I'll go ahead and add to the directions for step number 5. I'm going to say, I like the word swing. Swing lone pair electrons from terminal atoms, those will be oxygen atoms, as necessary. I'll go ahead and say to form that other type of covalent bond, which we call pi bonds. So here's how this works. And I'm actually going to kind of use step 4 structure to kind of lead us into step 5. So what I'm trying to say there is, and it's totally legit, if you can take any of these, like you can take north or south or west, any of those lone pair electrons and swing them in to become a pi bond. Well, that yellow doesn't really do it very good, but hopefully you see the yellow. So actually when I redraw this structure, it's going to be oxygen with 2 pairs, not 3 pairs now, double bond carbon. So, but when I do that, carbon only has, not quite ready yet, right? Carbon, swinging that in, still just 6 electrons. So I got to do that with the other oxygen too. So applying that last step then, we end up with actually a final Lewis structure where it says carbon, double bond oxygen, and now that oxygen atom only has 2 pairs of lone pair electrons, double bond oxygen. And the other oxygen actually, after swinging a pair of electrons, only has 4 or 2 pairs of electrons. So one of the things on your lab that we're going to kind of talk through is once you draw your final Lewis structure like this, make sure each atom has a complete octet, or at least a rare gas configuration, or if it's boron, 6 electrons, right? So as we draw the circle around that oxygen, we have 2, 4, 6, 8. So that's cool. If we draw a circle around the carbon atom, 2, 4, 6, 8. We draw a circle around that oxygen atom, 2, 4, 6, 8. So they actually all have a complete octet. So that's just kind of starting from the beginning, drawing a Lewis structure for something. So let's take a look at part 8 now. Parts is parts. So this is a list, and some of these you're already familiar with, and some of them you aren't so familiar with. But once you get your final Lewis structure drawn, like we just did for carbon dioxide, and which we did for the formate ion in Monday's lecture, and which you guys are going to do in lab tomorrow, you can actually knock out all of this stuff. Looks like a bunch of really cool stuff from your Lewis structure, if it's drawn properly. So, talking about bond properties, and you'll see what I mean. Now, these are covalent bond properties. In general, and this makes sense, some of these are more intuitive than others. Boy, they must have a lot of gum. Oh, I know what they are. They're like little kiss wrappers, because we have a sweet little teacher going around giving out kisses. In general, if you have the same 2 atoms that are bonded together, the higher the bond order, or the more covalent bonds between them, the stronger the bond. Okay? Triple bond is stronger than a double bond, is stronger than a single bond. And it kind of makes sense. I almost think of somebody doing like a karate chop, you know. That makes sense. But the other thing maybe makes sense to you too. When it comes to comparing, this would be, again, between the same two atoms. That secondary bond, the pi bond, is much weaker than the first to arrive. Remember, sigma bonds are your meat and potatoes. Pi bonds are your kind of leftovers. So here we have, if your two atoms are carbon, then the carbon triple bond is the strongest and the carbon single bond is the weakest. So I'm hoping you remember all that we talked about in yesterday's lecture with regard to sigma and pi bonds. Remember this triple bond, any triple bond is 1 sigma and 2 pi. Any triple bond. This is 1 sigma and 1 pi. Of course, this is 1 sigma. Okay. So this chart is kind of busier than we necessarily need it to be, but this is just trying to emphasize if you kind of chop it up this way, okay, because you have to make sure that you're comparing the same two atoms, okay, then actually you can go ahead and make some comparisons with regard to the single bond or the triple bond. By the way, the second slide after the introduction slide, the first slide after the introduction slide, talked about something called bond order. And all bond order is single, 1 is equal to single, okay, 2 is equal to double, 3 is equal to triple. Okay, so the bond order then, for instance, in this middle segment, this is bond order 1, 2, and 3. That's all that means. So if you draw your Lewis structure, you got bond order. What's it mean? It means single, double, or triple between the atoms. So bond length, then again, we're talking about the characteristic of these covalent bonds. The triple bond is the shortest, and the single bond is the longest. Okay? Triple bond is the shortest, and it will be shorter than double bond, which will be shorter than a single bond for the same two atoms. Then another or separate characteristic is this. Okay, this is now comparing different types of atoms that are bonded together with the same type of bond. Okay, this says that, you can read it, but it says that if the size of your atom increases, then the distance between them will increase. Okay, so the size of your atom increases, the bond length between those two atoms increases. So we have kind of a slide here I have some data coming up. So this is to say your triple bond is shortest, that's on the left, and your single bond is longest. So bond order of 3, 2, 1. Again, we can't confound things, so we're isolating, the situation to the same two atoms bonded together. So this one looks at that second property where the larger the atom, the longer the bond length. So if you want to kind of pick on something, we could pick on the halogens, the group 7A elements. Okay. They're good to pick on because we know that size increases as you go down. And so they're listed, of course, fluorine's the smallest, chlorine, bromine, iodine. So can you see that the distance between these halogens and their hydrogen atom they're connected to increases? And here, actually several of them, is kind of showing you the trend between bond orders. So the triple bond is shortest and the single bond is longest. All sorts of good things there. Okay. So another thing, if you have your Lewis structure properly drawn, is you can knock out what sort of orbital hybridization an atom has undergone as it's connected with covalent bonds to another atom. So orbital hybridization, start thinking of them in terms of a particular atom. An atom of interest has undergone orbital hybridization. What it is hybridized is its atomic orbitals. So we talked about atomic orbitals. So atom A wants to bond with atom B, and what we're going to see is it takes some of its individual atomic orbitals, it hybridizes them, wonderful thing, okay, and it sends out different atomic orbitals, hybridized atomic orbitals. Okay. So, and this idea of a hybridization, you do it all the time in biology. I mean, the whole pea thing, you know, the characteristics of peas and crossbreeding them and all that, okay? You like a particular trait of this breed, a particular trait of this breed, you bring them together, you get something different. That's the process that this atom's undergoing. So we're going to see that this atom, it's like they have intelligence, right? I know, they don't, but what they call it, metamorphosis? I don't know. Anyway, it's some sort of thing they do in English where we put human characteristics on something that's not human. But the atomic orbitals that we're going to see the atom hybridize are S, P, and D. It's atomic orbitals. All right. So some things to kind of keep in mind as we talk about this atomic hybridization process that atoms undergo as they prepare to bond with another atom. The number of hybridized orbitals, I say it spits out on the other side after it's undergone hybridization. The number it spits out is the same number as the number that it took in internally to hybridize, to mix it up. Okay, so if it took 3 of its atomic orbitals, hybridized them, it gets 3 hybridized orbitals out. Okay. This one down here kind of reminds me of biology too. Okay. We're going to see, for instance, there's something, a hybridization process called SP, and there's a hybridization process called SP3. So in one case, it takes one of its S and one of its P, that's SP. In another case, it takes one of its S and 3 of its P's. So guess what? The SP3, it's got more P characteristic than the SP. Okay, again, it's like biology. Okay, stronger traits come out. So one of the cool things that actually science, chemists or whoever's doing it, has found out that at the end of this hybridization process, those hybridized orbitals are equal in all characteristics. Okay, it's kind of fun. This is an important one. When we're talking about hybridized orbitals, those hybridized orbitals can only participate, sometimes I'll use that term, be associated with sigma bond electrons and lone pair electrons. That's it. That's it. Okay. Pi bond electrons cannot occupy hybridized orbitals. They're left out. So on a Lewis structure, if you're looking at something that, an atom, and you're saying, oh, I wonder what sort of hybridization that atom has done, well, the things you look around that atom from that Lewis structure is you look at the sigma bonds and you look at the lone pair electrons. If you're looking at a final Lewis structure and it happens to have a double bond or a triple bond, so you have 2 or 4 electrons that are actually then participating in this pi covalent bond, they are hanging out in unhybridized p orbitals. So they aren't special, so as to speak, in this sense. So there are actually 5 different, I think only 5, but 5 different ways that an atom can take 2 or more of its atomic orbitals and hybridize them. We are going to focus on the first 3, but I'm going to show you the other 2. So the first 3 are most important. You're going to see them on a test, and we're going to focus on them tomorrow's lab. So in the first case, the atom takes one of its S and one of its P. We call that sort of process SP. And due to the conservation of orbitals, it's going to spit out 2 hybridized orbitals, etc. SP2, it takes one of its S, 2 of its P's, spits out 3 orbitals, hybridized orbitals. SP3, it takes one of its S and 3 of its P and spits out 4 hybridized orbitals. The other 2, remember when we talked about expanded valences? Yeah. The other 2 situations are exciting, where an atom takes one of its S, three of its P, and one of its D. sp3d. So that's a total of actually 5 hybridized orbitals. Let me go ahead and kind of clarify then what that would look like on the Lewis structure. What you're going to see here is instead of an octet, you're going to see actually it has a set of 10 electrons around the Lewis structure. Take it up a notch, sp3d2. That is actually going to have 12 electrons on your Lewis structure. And you're going to see that it has 6 hybridized orbitals. Just itching to either participate in sigma bonds or lone pair electrons. All right. So I already said this. The whole idea of the hybridized orbitals, whether it's 2, 3, 4, or 5 or 6 hybridized orbitals, they're all equal, which is kind of strange. A little bit, I think. And I'll kind of show you why it is kind of strange. So if we pick on methane for a little bit, methane is a central carbon atom, that's the black atom, and then 4 hydrogen atoms spreading out from that central carbon atom. So if we focus on carbon, see, here's the deal, here's the problem. That carbon somehow has 4 electrons that are actually participating in a pair of electrons that are participating in a sigma bond. Those are sigma bonds, right? So we have 2 electrons here, sigma bond, 2 electrons here, sigma bond, but they're all equal. You're like, well, why would that make a difference? Well, if you look at carbon, the electrons around a carbon atom are configured this way. So it would seem that actually those 4 valence electrons, 2 in the 2s and 2 in the 2p, you're like, dude, it should be a little lopsided when they come to connect up with the hydrogen atoms. Okay? We do know that the way we configure electrons need to go in the lowest n plus L, completely fill that subshell. Okay? But we know that actually if you zap it with a little bit of electricity, you can actually go ahead with energy, go ahead and promote an electron up. So this actually, one of the homework things that you guys did is to say, for instance, what's wrong with the second configuration? It's an excited state. Why? Because you fill the subshell first. Okay. So let me kind of show you this hybridization process, or I'll let her show you. I think she does a good job.
The valence orbitals of carbon are the 2s orbital and the 3 2p orbitals. When these atoms form methane, their orbitals are thought to hybridize to form 4 equivalent orbitals. Because each hybrid orbital for the carbon atom is composed of 1 part s orbital and 3 parts p orbital, they are called sp3 orbitals. The energies of the hybrid orbitals are the average of the original atomic orbitals.
Isn't that cool? It explains why each of those bonds between hydrogen atoms are the same. And, you know, this is just one example of orbital hybridization. So this is kind of showing you how, you know, at the top there are the unhybridized orbitals. Okay, so these are unhybridized. Oh, goodness. One of the things we said, with regard to S are all spherical, whether it's 1s, 2s, 3s, etc. P are all dumbbell shaped, so that's what you're seeing over here. These are the dumbbell shaped of P. Okay? And so this is talking about sp3 hybridization. That central carbon atom has 4 equivalent hybridized orbitals it's spitting out. And this actually then is kind of a cross between that single S and those 3 Ps, but check out all the dumbbell characteristic it has. So it really takes on a strong characteristic of the P-type subshell. Okay. And then this then is kind of if you combine these 4 hybridized orbitals around carbon, this is kind of what they look like. So methane, central carbon atom, 4 hydrogen atoms. Remember that the way covalent bonds form is basically an overlap between atomic orbitals. So now we have the carbon is not just regular atomic orbitals, they're hybridized atomic orbitals. And the overlap that I described the other day is kind of right here-ish. Okay, that is the overlap. Atomic orbital of hydrogen in gold, hybridized atomic orbitals of carbon in blue. Let's see, this one does too. It's like, you know it's safe. Go ahead and open it.
A methane molecule forms when 4 hydrogen atoms form sigma bonds to the sp3 hybrid orbitals of the carbon atom.
Yeah. I approve. Okay. So I told you 4 that you need to know. SP, SP2, and SP3. I just talked about SP3. This is SP2. I know this is SP2 because from the law of the conservation of hybridized orbitals, it's got 3 blue things. Those blue things are hybridized orbitals. So that central atom, which we don't say what the central atom is necessarily, but that central atom has taken 1 of its S and 2 of its P's, SP2. Okay. And it has spit out 3 hybridized orbitals. SP2, SP2, SP2. So similarly, this little video is there's no video. But this is showing you how an atom has S orbitals and P orbitals. And to get these sp2 hybridized orbitals, it takes its one S, and then it brings down 2 of its P's, okay, to create these 3 hybridized orbitals. The last one, we're kind of going backwards, aren't we? Because we went sp3, sp2, this is sp. Okay, so what it spits out then are 2 hybridized orbitals that can be used for sigma bonds or lone pair electrons. Okay. And notice finally here, I can't necessarily tell it, but you would think this would have the strongest S characteristic as compared to the sp3. Now, I've kind of glossed over kind of these 2 right here in the last 2 slides, last 3 slides exactly. But I'll get to it. That is shape around the atom that's undergone orbital hybridization. So this is showing you how an atom with S and P orbitals available takes 1 of its S's and 1 of its P's, and it has 2 equal hybridized SP orbitals. Okay, so now on to shape. And this is why I brought my little toys here. So, it's an acronym. Yeah, I looked it up on the internet. So acronym is this. Basically, each letter stands for something important in this physical science thing. Okay, it's called valence shell electron pair repulsion theory. Okay, and sometimes acronyms are more important than others. I think this one is one that says a lot in valence shell electron pair repulsion theory. We've been talking about valence shell electrons, basically a pot of electrons. We did that with carbon dioxide, a pot of valence electrons. Okay, and we've seen those electrons go in pairs, go in twosies, whether they're lone pairs okay, or whether they're participating in a sigma bond, 2 electrons, or pi bond, 2 electrons. So that's the pair. The repulsion theory, I get all excited about, because the repulsion part is what gives the atom, gives shape. I'll just put shape. Okay, the repulsion part is what gives shape from around the atom. I'll just leave it that way. The repulsion part. Valence shell, electron pair, repulsion theory. Nice ring to it too. Valence shell, electron pair, repulsion theory. I call it Vesper, which is not really right because the S and the E are in the wrong order. Okay, but Vesper theory. I think I've heard other people call it that way. So it picks up where we left off. We said that hybridized orbitals, okay, we said hybridized orbitals that an atom has prepared, getting ready to bond with another atom. We said that actually that those hybridized orbitals can only participate in sigma bonds and lone pair electrons. Sigma bonds, lone pair electrons. No pi bonds. So actually, no pi bonds give shape. Exclamation point. Final Lewis structure, you count pi bonds, they don't give no shape. Okay? So the repulse part is kind of fun. The repulse part is basically those sigma bonds and lone pair electrons are going to repulse as far apart as possible. And so those shapes that you saw a little bit ago of the sp3, then sp2, then sp, actually that's kind of the shape we're going to see. That was a purposeful shape. It's called actually tetrahedral, trigonal planar, and linear, respectively. So I brought, and I think we'll kind of be referring to them, I brought these in that we had the other day. Okay, so this is C2H6. This is C2H4. So those are the weak wimpy pi bond. That's one pi bond, excuse me. It's a pair of electrons making that purple and pink. Okay. And this is your C2H2. Okay, so we have sigma pi pi. And those pi electrons that make that secondary covalent bond, they don't give shape around the atom. So valence shell electron pair repulsion theory. So if you have two things around any atom, the best they can do to get as far apart from each other as possible is this. Okay. So SP hybridization of that orange atom would send out two equal hybridized orbitals. When they repulse from each other, whether they're a sigma bond or lone pair electrons, this is what they're going to look like. Okay, we call that linear. SP3. SP3 looks like this. And sometimes I'm like, no, they can get farther apart than that, but no. Mathematically speaking, when they try to repulse as far apart, and you can actually do this with balloons, after you blow them up, you kind of take 3 balloons and kind of hold them where the blow-up part is. To get as far apart as possible, they're going to lie in a plane, okay, and they're going to look like this. We call that trigonal, and it lies in a plane, trigonal planar. I've seen a lot of different spellings for trigonal planar. So that's SP2. SP3 looks like this, and it's tetrahedral. So it kind of looks like a pyramid. So actually this black ball is set up to have 4 things sticking to it, whether they are sigma bonds or lone pair electrons. And the farthest they can get apart from each other is a shape we call tetrahedral. I said that right, tetrahedral. So the fact that it has 4 equal hybridized orbitals means that it must have undergone sp3 orbital hybridization. So there you go. Tetrahedral. It's a lot Do you have those words? Okay. So linear is SP. And by the way, I bet you're hopefully trying to already pick up on this. When we talk about, and there's a word coming up called electron pair geometry or structural geometry, we're actually looking at a particular atom, counting sigma, that primary bond, and lone pair electrons, and judging what sort of hybridization process is undergone. And in all doing so, we can actually go ahead and get to the shape, according to them repulsing as far apart as possible. So structural geometry, electron pair geometry, it's the same thing. To emphasize what it's not, I'll put it at the bottom here. I'll say this is different from molecular geometry. I'll put geometry of the molecule. How's that? Geometry of the molecule. This is on a large scale, the geometry of the molecule is on a large scale. But actually, you can use this to get to this. So they're not entirely disconnected. Basically, what you need to go is electron pair geometry to electron pair geometry to electron pair geometry all around the molecule. And then you basically have lifted that Lewis structure off the paper and made it real. Okay, there are some cool, like, it's called augmented reality or like 3D. Basically, you put on glasses and you kind of manipulate things, you know, just like the Matrix. So what we're talking about and what we're going to spend most of our time is basically the structure around an atom. Okay, so the three hybridizations that you need to be familiar with, be able to wrap your mind around, we're going to work on these tomorrow, is if an atom has undergone sp hybridization, sp2, and sp3. I already kind of told you the shape is linear, trigonoplanar, tetrahedral up here. Then this is also kind of good information. And this, again, is kind of like if you want to look at an overall molecule, has lots of atoms, right? You would have to go individual by individual, and you would actually know how the angle is with at each vertice between the atoms, okay? So this probably makes sense. Does this look like a 180 degree, okay? And this actually is 120 degrees, because the circle is 360. And this is 109.5 degrees, tetrahedral. Okay. So, these are the ones you need to know. Let me, just for kicks, no, I got some pictures coming up. I got some pictures to show you what these two are. Okay, so this is sp3d and sp3d2. These are examples of sp3, I guess I should point here, sp3d and sp3d2. I got some good pictures coming up. So I mentioned you can kind of convince yourself about this whole repulsion thing if you go ahead and blow up balloons and hold the balloons at the blow up part and let them repulse as far apart as possible. Okay, and you'll come up with these structures. Okay, we're missing sp here, but of course this is sp2, sp3, and this actually is sp3d. That actually is called trigonal bipyramidal. So you can kind of see the trigonal part, and it kind of goes up like that. Okay. And okay, I couldn't remember octahedral. That just doesn't seem right to me. So the last one up here, the yellow balloon, is sp3d2. Conservation of orbitals. Okay, so let's see, 1 plus 3 plus 2, so that must mean 6. Okay, so actually, if this actually is the atom that's undergoing the hybridization, can you see 1, 2, 3, 4, 5, 6? Okay, and this is called bipyramidal. No, octahedral. Final answer. Because I cheated. Okay. But that is actually how the sigma bonds or lone pair electrons are oriented in space around an atom that has done that. So again, kind of from left to right. Finally, here you have your SP, SP2, SP3, SP3D, SP3D2. So right. So right. So then actually these are kind of interesting because they go ahead and give examples of they aren't necessarily all molecules, but where actually the central atom has undergone this sort of hybridization. Now here your author's kind of clever and points out the fact that remember that those hybridized orbitals, for instance, that A is sticking out, kind of represented by the white stick, those hybridized orbitals, in this case overlapping or connecting with orbitals around atom X to create a bond. Remember that those hybridized orbitals can also participate in lone pair electrons. Now this is where students are kind of like, well, does that give shape? And yes, that does give shape. Do you see the repulsion part in electron pair repulsion theory going on here? Okay, so this, and sometimes these are called electron domains, is actually giving shape to the, or geometry to the atom. So SP3, that was SP2, this is SP3. Again, we could kind of look at some situations in which those hybridized orbitals are not participating in a sigma bond to another atom. They're actually participating, or a location where a pair of lone pair electrons hang out. And SP3D, 5 hybridized orbitals. 5 hybridized orbitals, that's your trigonal bipyramidal sort of thing. It's tricky though, because check this out. You know, here we have basically it's an A-B2 sort of situation where the electron pair geometry really is actually SP3D, but it could look like something else. Last but not least, SP3D2. Some possibilities of, instead of covalently bonding to an atom, a pair of lone pair electrons are hanging out in that hybridized orbital. So again, we are going to focus on those first 3 types of orbital hybridization. But for homework, I'll put HW here. For homework, you might need to dabble in those. Good deal. Let me see how many more. I think this is all good. So what we're going to do is I think tomorrow in lecture, I'm actually going to kind of jump ahead. Those last few slides where you have kind of the circles on your Lewis structures, I'm going to pull that up tomorrow, and we're going to talk about how, if you're given a Lewis structure like you have at the end of this part 8, how do you go ahead and for the atom in question, knock out the orbital hybridization and that sort of thing. So I'm going to pull the, you don't have to bring it to, but you do need to bring your lab notebook, but you wouldn't have to bring your lecture notebook. Okay, see you tomorrow. Oh, does it say it's Saturday and the time is wrong? I didn't even notice. I was like, well, I don't know.